Um, Anything to discuss from the homework or anything else? Any questions? No. Um, so actually, we will go through an important topic. Uh, yes, I'm not sharing. So we will actually go think through, we'll see how far we'll go, but actually two important topics. So even if the first will be selecting time histories. So even if sort of someone else has performed the seismic hazard analysis for you, how do you select appropriate time histories uh, to use in your analysis? And some options that you have also in terms of modifying them. And then the next topic, if there is time, would be on going through the software. And I think I still haven't finalized assignment too, but I will do it before the weekend. And so in the weekend, it may be worthwhile going over it, and then we can discuss it on Monday. But I think there will be three problems. One will cover a little bit the magnitude, the time-dependent models that we discussed maybe a lecture or two ago. The second will be a more comprehensive seismic hazard analysis. So I think in the first assignment you did it for three scenarios that are discrete. Now we will have like distributions to define their magnitude and the locations to kind of go through the process manually. And then the third problem will be running a similar problem, but in a PSHA software, where that's how you will do it if you were to be tasked with with like carrying such an analysis in practice. So regarding the time series, so let's let's connect it with where we currently are. So with what we have covered so far, we should be able to get a design spectrum. So that's the spectrum that we get for the return period that we are interested in. And it can either be based on the hazard or based on its risk. And also we saw how we can go and use either like a uniform hazard spectrum or something like a conditional mean spectrum. So assume that we already have that. Um, and we also saw last time how we can do the aggregation. So we can get the parameters that describe this scenario, so the magnitude and the distance that is most closely associated with this scenario. Then we saw how we can get other parameters that further characterize the ground shaking using like either conditional or other types of the ground motion models to get like some sense about the duration, the iris intensity, the PGV. So we have a lot of information that characterize the ground shaking, but if we were to this information on its own as it exists here, it may be useful for some applications. So if someone runs like spectral type of dynamic analysis, then all you need is the distribution of these parameters. But if you have a more sophisticated model that requires like a time domain numerical solver, then you need to have a time history to put as input. So now that we have characterized the ground shaking, we need to find time histories that are consistent with the scenario that we have identified contributes to our hazard and use it in our analysis. So that's the goal. So again, the input is we have the uniform hazard spectrum, we have the aggregation, and we know the scenario that is contributing. So we know magnitude style, folding distance, and so on. And we plug these numbers into like conditional models and we get the distribution for the PGV. So we have the median value, we have the standard deviation, so we also know a range for that, for the peak ground velocity given the condition, the scenario of interest, the durations and so on. So there are different databases that have where you can use where you can search for time histories to run your analysis. And the biggest one for engineering applications is the peer database. So I formulated the example around that. So if you can go to Peer's website. So is it Peer NGA database? And again, if you remember, we talked about the different tectonic environments. So if we are performing a seismic hazard for a site that is in a like shallow crustal area such as California or Oregon or in general the West Coast, then we'll go to the NGA West. If we care about like a project, we perform the seismic hazard analysis for a project in a stable continental region, then we'll go to NGA West, and this is ground motions that are recorded for like from the eastern United States or other regions with similar tectonic environments. And then there is also currently an undergoing effort to develop the NGA sub. So that will be the database for a subduction type event. So we can go to the appropriate database, create an account, and then here we can and we can use now the the search form to identify the appropriate ground motion. So I went ahead and took some screenshots of that to go through an example. So we have the uniform hazard spectrum from our analysis, and we can go ahead and save that in a TXT file and load it. And then in the next page, we can define the magnitude range for which we want to search, the distance, and some other information like the VS30, the duration, and so on. How many records we want to select, and how we want to, like, it will go through its entire database, and for these filtering parameters, it will go and score all of the ground motions based on how close they match our spectrum. So we can also define how we want to score and how we want to apply weights for the for fitting. So here we are saying that we want to fit the periods from 0.1 to 10 seconds and apply equal weights for all of them. So if we click next and it goes through the database, it will find that the 20 time series that have the smallest error with respect to the objective function that we have defined. And I believe, for example, you have done this before. Okay. Anyone else who has used this tool in the past? Okay. Any information, any other thing that you would use in the selection? And once we have this, so these are all the time series that are scaled with some constant value. but are but have the smallest, like they are ranked based on their error with respect to how well they match the input spectrum for the periods that we have defined. And we can go, and we can also click one by one and see how they compare. So we can see both how they compare in terms of the scale version. So we have the recorded time series, and if we multiply it with a constant, then we can essentially take the entire spectrum and shift it up or down by that constant. So we can both compare the original spectrum with what we are trying to match, and this shows us like sort of the scale factor in the amplitude that needs to be applied, but we can also see how the shape in a normalized way fits with the input spectrum. And here is the scaling factor. So for example, the first ground motion needs to be scaled by a factor of 11, some needs to be decreased by a factor of 0.8, and some needs to be increased by a smaller scaling factor. So one of the things that when you go through this process is deciding sort of what scale factor should be used and whether it's reasonable or it may lead to ground motions that are unrealistic. So there's some debate in the community. Some people are trying to limit scale factors to be between 1/3 and 3, like not scaling a ground motion tremendously, because otherwise they think that ground motion is not representative of the scenario that you are trying to fit. But then there are other people who feel that there shouldn't be any constraints that you apply in the scaling factors, as long as you ensure that all of the parameters of the time history that you have selected are still consistent with the scenario that you are trying to match. And you can tell us if you have any sort of, in which camp you fall, or how do you select time series? Does that sound similar, or we follow a different process?
I think we didn't do exactly scaling. So what I did was I was looking at all the ground motions that have been recorded in NGA East in the last like 40-50 years, and I was doing a qualitative study. So there are like maybe just 3 or 4 ground motions that exceeded 0.2 G. So most of the ground motions were less, PGA was less than 0.2 G.
Okay.
So it was like a qualitative study to finally conclude that in East, we are not supposed to design for a ground motion of magnitude maybe 7 or 8, because nothing has been recorded in the last 40 years. So the probability that a ground motion with PGA greater than 0.2 G would be recorded is very, very, very less.
Correct. At the same time, when we're evaluating the hazard, we're evaluating like for ground motion that may happen once in 500 years. So
and also like there is mention of that, like some earthquakes like Charley Voice, something like that. And those earthquakes, they came in like the 17th century, 1667 or something like that. We didn't even had the proper instrumentation to record those earthquakes. How can we say that it was magnitude 7.5 or it was magnitude 8? It was just qualitative.
Yes. So. Yeah. Okay. So yes. So like that's maybe another way that you can filter the ground motions. Like if you can say, so I'm guessing like essentially you force the scaling factor in that case to be 1 and looked at like the PGA, right? And you applied a weight of 1 essentially. Yeah. When we sort of in deciding also how much we want to scale its ground motion, we also need to think like different scaling factors. I'm sorry, different parameters are influenced by the scaling factor differently. Why is that the case? So like the scaling factor is essentially what we say is like the acceleration time history that we want to get is some constant c, the scaling factor, times the original time series, right? So that will linearly increase all the amplitudes of the time series, but what will do to its duration? So its duration will be unaffected by the scaling factor that we apply, because we see how the duration is based on like this normalized areas intensity. The areas intensity, AI, is the integral of the acceleration squared times, like it's proportional to the integral of the it's 1/2 pi times that. So applying this factor of c will be the areas intensity will be increased by that constant squared. So typically, there is the belief that we shouldn't use very large scaling factors because there are other processes that we may not have well characterized for the ground motions. And so when we are applying very different, very large scaling factors, we are influencing that. But what is more important is sort of understanding what it is that is actually important for our structure, and then properly characterizing it. Also, you can be how close, like the range that you need to apply to scaling factors also depends on how strict you are with the filtering criteria that you apply. So we saw in the very beginning, we need to specify here the range that we want for magnitude, for the distances, for VS30, duration, and so on. So if we put very strict criteria here, then there may be not many ground motions left. And so the ones that are left, we need to apply large scaling factors. But again, we kind of need to think of what it is that we are doing. So if in the end, what we want to do is have a ground motion that has a constant, a consistent shape with our target spectrum, and these parameters are indirectly influencing the shape of the spectrum itself, then filtering the ground motion based on this parameter, but also trying to match the spectrum is sort of, both of them are after the same thing. So if the goal is to simply fit the target spectrum, we can have much wider range for these ones, and then still filter and still identify the ones that work best and use them. And kind of to show why sort of there may like this sort of very strict belief that like the scaling factor needs to be close to tight around 1 is not necessarily a valid assumption. Here I'm showing two ground motions, the response vector of two ground motions. One that have been scaled by a factor of 28, so that's like sort of like an extreme case where the original ground motion is significantly different from the target spectrum, and one that is scaled by a factor of 1.3. But we can see if we are properly scaled, then both of them are fitting the target spectrum quite well. And if we look at their time series, like so, this is the acceleration time series and the velocity time series for the two spectra. So like if one of them is scaled by a small scaling factor, so we will argue that it's realistic, and like we couldn't really say which, like by looking at them, which one is sort of realistic and which one is unrealistic because it has been applied by a large scale factor. Like can any of you tell me which one is the one that's been correct, that has been multiplied with like a factor of almost 30, and which is the one that is closer to its original scale? Any idea?
There is one approach that maybe we can do the Fourier analysis, and we can see that it is like there is a lot less high frequency content than it could be like the 12 one, and if no, the 41, and if there is a high frequency content, then it would be the 12 one.
They both have. I don't have the free. I can try to find plot the frequency. Yeah, I didn't plot the full amplitude, but I plot the response spectrum, and they are matching. So I'm expecting the Fourier amplitude will also have will be similar. For me, the only way to tell which is which, maybe if you go back to lecture one, we talked about like P and S waves. So this is like the P wave, the first wave that arrives, and these are like the S waves. So the secondary waves, and those are the ones that carry the strongest ground motion. And here, this is like where the P wave, no, here, this is where the P wave, and this is where the S. So the distance between the two, the time delay, is telling you something about the distance. So this is the earthquake that this is the ground motion from an earthquake that is over a larger distance. But other than that, in terms of like its frequency content, they are actually quite similar. So if things like that matter critical structure, then you should try to explicitly like account and model and filter the ground motions based on them. But if you say if features like that are irrelevant, then both ground motions will be valid for the structural analysis that you would perform. Yes.
On the P wave, we see that the acceleration is quite less, and then we say that the S waves come and the acceleration increases. So is that like because both P and S waves are there, or like S waves, like if we subject a structure to just P wave, then maybe we will see less acceleration, and just S waves, then we will see more acceleration. Is there something like that?
So if you subject a structure to P or S waves, like the time histories that we have recorded have both. So you are saying like filtering and keeping one of them?
Yeah, so my question is that will the displacement of the structure be greater if it is P wave versus S wave? Or is there, is there an influence of the type of wave?
So S waves tend to carry more energy compared to P waves. So if you remember, like when we had like if you're trying to plot like the area's intensity evolution, it will look something like where it will be increasing, and once you go to the S waves, it will start increasing a lot faster. So, and if you think that like the amplitude squared is sort of proportional to the energy in the ground motion, then most of the energy is contained here. So, like your structural response is going to be influenced by this part of the ground motion, mostly, not so much about from the from the from the P waves, because they are much less in amplitude. Is that or?
Yeah, so basically, I think that this means that S waves carry more energy than the P waves.
Yes.
So ultimately, they lead to more, maybe.
Correct. And if you have like if not so much in the West Coast, because we tend to the hydrogen is dominated by sources that are very close by, but here, like remember the third type of wave that we have is the surface waves. We don't really see maybe yeah, this one. No, these are the velocities. Like these are sort of the surface waves, but at larger distances, because they attenuate slower than the rest, most of the energy will be carried by the surface waves. So, like for those cases, maybe actually like the surface waves will be more important. And oh, one more thing. All of these things that we're discussing is if our structure is mostly sensitive to acceleration in the horizontal component. In the vertical component, P wave will actually may be the largest amplitude, but typically, like for irregular structures, they are more like the inertial loading on the horizontal component is more important, because like in the vertical, you already designed for the gravity load, and you don't really change. So this sort of like a summary that like scaling factor is something that maybe if someone asks you to select time history is one thing that you should be mindful of, but shouldn't be the entire reason on how you select time series. Okay, so then since we are already selecting time series based on the spectral shape, someone may say why simply scale the time series by a factor and why not like modify it slightly so that its frequency content better matches the target spectrum. So here as an example, um, we we select a time series that is more consistent with the target, but we can also think that if that's our goal, then we can like add some noise into the time series or uh, or process it so that it gets even closer to the target spectrum. Um, oh, I'm sorry. Before that, uh, another issue in selecting time series is sort of how much like there is variability um between the target and 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 the time series that you're selecting. So how much variability should actually be there and what variability should be removed. So one thing to keep in mind is that this target spectrum was developed for the median ground motions. So the variability in the median is already represented in the spectrum itself. But the variability from each component to the median is not. So that's something that would be accurate to be part of the of the of the selection. Um, Similarly, there if we were to go through a site response, and there will be additional variability that will be introduced because the amplification that we get for that site is different from the VS30 amplification. And similarly, this is not something that we accounted in when we run the hazard, so it's something that should be there. And ultimately, this is important. It's like all of these decisions depend on our final objectives. So if variability in the ground motion is something that is influencing our structural performance, then it's something that we need to be carefully in characterizing and including in analysis. Versus if it's not, where we can simply uh, suppress it. So to show And so depending on how much we want to maintain this variability or not, we have different ways of selecting and then processing the time history. So if we do what we already covered, where we simply scale the ground motions, then and where essentially we multiply the entire frequency range by the same constant, then we maintain all of the variability in the ground motions. Um, if we want to modify the time histories, then we can go through different options to modify the frequency content so that we bring the spectrum of each time series closer to the target. And that is suppressing part of the variability. And depending on like whether we like want to tightly match the target spectrum or whether we want to loosely match the target spectrum, we suppress different components of the variability. Like we can say that we want that the average horizontal component is tightly matching the target spectrum. And in this case, we are only left with the variability between the two components, or we can loosely match to the target spectrum. And in that case, we also have the variability that comes from the spectral shape of each ground motion relative to the smooth target. And sort of the most extreme case in terms of like filtering the ground motion is making sure that each time history is matching the target spectrum exactly. So to show that, imagine again we have some scenario for which we are fitting, and we get the time history that we have selected relative to our target spectrum. So what we can do is modify that time history, alter its frequency content slightly by adding different wavelets that we will see next, and going from the red spectrum to the green spectrum. And in this case, essentially what we are trying to do is make the least adjustments to the time histories, but still trying to get to alter its spectrum so that it best matches our target value. The way that this analysis works is you have the actual spectrum of the time series, you have the target spectrum, and you can calculate the difference between the amplitude of the spectrum of the ground motion and the amplitude of the spectrum of the time series that you want to map. And then you can introduce a pulse at that time where this spectrum happens in order to essentially counteract this effect. So if you have this pulse contributing to your spectral acceleration, you can sum your original time history with a pulse like that looks like this, and this amplitude plus this amplitude will bring the amplitude of this ground motion to the spectral acceleration that you are trying to match. One issue that we have is that the response spectrum is the peak amplitude in the response of the oscillator. So even if we suppress the largest pulse, there may be other pulses that still exceed the target spectrum, and so this is an iterative process that we need to do over and over again. And there are a number of software available that can help you do this analysis if that's something that you need to do for a design project. Yes.
Like for a particular period, if we want to match the target spectrum, then we are just introducing an artificial response and then superimposing.
Yes.
Wouldn't that be like just changing the properties of the ground motion problem?
It is. So at the end, you will still go and check that the new time history that you have is consistent with the properties of your conditional of the scenario that you are trying to match. Yeah, so that will happen.
I'm not able to like get it because this is, I think, the oscillator response at a particular period. So how do we go from oscillator response to the initial ground motion? Because this is like for a particular period structure, maybe.
Yes. So you are going to do that for every period that you want. So for every period, you will like you will start from the typically highest period to the smallest one, because as you are changing, like uh, the highest periods are like, if you change the small periods, the high periods will change, and so you're going from high frequency to small frequencies, and then in each one of them you calculate what is the difference between uh, the the actual response spectrum and the value that you are trying to fit, and you are adding a pulse to negate that difference. And then once you do that, then you go to the next frequency. So you are asking how do you do it? So like the the correction that you are applying is so the how can we write it? Like the here. The correction that you have is simply the impulsive response of the oscillator times the correction in the acceleration that you want to apply. So this is what you are modeling as a pulse. So this is actually a pulse that looks like this. And if you were to multiply it with the response of the oscillator, then it would be a wavelet that will have a shape that would look like this, with like depending on the damping that you have. And you will try to use essentially fit this shape with the response of the oscillator so that you reduce the amplitude of the original time series. So you're right, like this is, so you're saying like here is the oscillator response and this is the correction that you apply to the time series. So that's, those two are not in the same space, right? Yes. Any other questions? And you also, it's not necessary that you all, or that you like, you can use any type of wavelet to for the correction that you want to apply. You can have like a simple wavelet that is like a one peak, but you can have like the more complex wavelets that influence a larger portion of the ground motion, and some of them are more optimal in achieving like so. You you can use a wavelet that is the inverse of this, and then the correction that you're applying becomes the delta function. So if the correction that you're applying to the time history is something that looks like this, sorry, and then suddenly stops, and then you convolve it with this one, like you can use a wavelet that essentially will the different peaks will constructively interfere so that you are left with a correction that is like more closer to a delta function. And that's something that you can easier do, but then this behavior may not be a realistic behavior for the correction that you want to apply in the time series. So there is a little bit of sort of a trial and error associated with it. And depending on the wavelet that you can use, it may be easier or more difficult to fit the ground motion and still be left with a realistic shape. Any other questions? So this type of analysis is something that you may want to do if what you are really after is characterizing the mean structural response of your structure, because you suppressed all of your variability. But if your final goal is um, also characterizing the variability of your structure, then maybe simply scaling the ground motion is a more appropriate analysis. And as an example, like if your goal is sort of to see whether your structure is safe or not against a single scenario, then like in that case, what you're really after is like on average whether you are safe or not. So like in that case, suppressing the variability is good because you can have a more robust estimate for the mean performance. But if you want to use some types of time series to do a fragility calculation and develop a fragility curve, then the shape of your fragility curve that you get, that is like for where you have the like, let's say PGA, and then the probability of collapse to get the actual shape, which also involves the probability, not whether it's one or the other, then maintaining the variability is actually important. Um, and again, this is sort of reasons for why this, although this method is like, I think even like in the previous version of the building code, it was highly penalized. It may still make sense is that the thing to be aware is like in any case, we are still trying to fit a particular spectrum. So in both cases, even if we are simply scaling the ground motion, we are reducing the variability relative to the full variability of the ground motion. So it's really a matter of how strict we are about that. So what we saw before is like fitting each ground motion to the target spectrum. But as we said, when we perform the seismic hazard analysis using some type of ground motion model, these ground motion models are developed for the average horizontal component. So the variability between two components is really something that we haven't accounted in our analysis. So it's appropriate to keep that variability in the time series. And as an example, so if we have the two components of the scenario that we want to use in our structural analysis, instead of taking each one of them and making sure that it fits to the target spectrum, we can modify them less so that when we take the average of the time users that are modified by a lesser amount, it is matching the average. So, like for example, we don't need to entirely drop this peak and increase this trough, but only slightly modify so that the average of the two is close to the target. And yes, so this is the example. So we can start with like the two ground motions that are on average that we want to match their average of the two, and then that would require a much smaller change in its components so that when the average is taken, we get a value that is matching the target spectrum. Any questions on time history selection and spectral matching? Okay, then we can also go through then the second part, which is the PSHA software. So in the second assignment, I think the third problem, I will ask you to run HALS-45, and that's an open source PSA software that you can use to perform probabilistic seismic hazard analysis. And like, so the goal of this class essentially is like we kind of went through the components and did some of the things manually. The idea is that you are aware of all these options that you have so that you can use a software like this to run the analysis. And why do we need to have PSHA programs is because like for the scenarios that for the first assignment and what I will ask in the second one, we go through like maybe 3 scenarios in the first or maybe 100 in the second, but when you really run a seismic hazard analysis, you go through thousands or tens of thousands of scenarios. So you don't want to do those by hand, you want to use a software to go through that, and something that is also able to track all of the uncertainties so that you can then take them into consideration when you give the final values. So this software has 2 modules. So the first file that you need to define is the one that is the seismic source characterization, and there is where you essentially use the things that we covered in the beginning, where you describe the earthquake recurrence for each source and its geometry. And then the second is the ground motion model, where which is used to define and then evaluate the ground motion models for all the sources that you have defined. And then after you do an analysis, you have different post-processing options to get the hazard curves, the uniform hazard spectrum, the aggregation, and the conditional mean spectrum, and also other options to quantify the uncertainties. So figure out which part of your analysis contribute to the largest uncertainty in your final answer, and that tells you which part of your analysis you need to further concentrate and refine, because that's sort of the critical aspect of your model. So as I said, in the 2 modules, you need to define the fault file, which will define the geometries of all the faults and background zones that you want to use. And then the run file, where you will define the ground motion models that you will use that are applicable to your scenario. The site conditions, so information about like the VS30, the depth to 1,000 meters per second or 2,500 meters per second, and where your site is located relative to all the faults to calculate all the necessary distances. So in the fault file, the information that you need to have to insert is the activity rate that either can come from like historical seismicity. So as you said, as we saw, like this can come by first evaluating the completeness, like having a historical catalog, figuring out its completeness, and then calculating the frequency of events. Or if you have individual faults where you know the slip rate, you can define the activity rate by balancing the moments as you did in your first assignment. And the last case, which it like depending on sort of the project that you are involved, you can also use sort of historical data to define the rate of individual faults. And the way that you do it is like typically geologists can dig a trench where the fault is located and find evidence of past events and carbon date them. So if you know how many events you had over like the last 500 years, the number of events times the exposure periods that you have will give you the activity rate for that event. But then you also need to be careful as to which is the magnitude that goes with these events. Because if you only can collect evidence for like large earthquakes, because you cannot see like smaller events will not leave large geologic evidence, then you really have the activity rate for like a magnitude 6 or a magnitude 7. So you need to adjust that value appropriately. Once you have the activity rate, then you can also define the full distribution for the magnitude. And again, it's all the mod, like all of this should start being familiar with you. Like we cover like the truncated exponential, I think you used that, or the Young-Copperfield, which is like the characteristic model, or the pure characteristic, which is a normal distribution around your characteristic magnitude, or some composite distribution like the one that we see that had a shape that was a combination of an exponential, like it was an exponential, then had a normal distribution, and then a second exponential tail. So you need to select which model you think is applicable, and then which relationship that you should use for the area and the width of your, to calculate the area and the width as a function of the magnitude. And again, we went, for example, we said that like the area, like a simplified relation to use is the area is 10 raised to the magnitude minus 4. So that should be one model, or if you know something like a better model that works, that is tailored to the fault that you are interested in, you can specify that instead. And similar, you can define how the width should scale with magnitude and what is sort of the maximum width that you allow. The reason that this needs to be specified is because for every magnitude that it will evaluate its area, its width, and then it has the full dimensions of the rupture relative to the fault. So then what it can do is, if this is your fault plane, and this is your rupture defined by like its length and its width, it will float the rupture over the entire fault plane and calculate the distances and the distribution of distances for all possible scenarios. You can also specify, and depending on how much information you have different options about the location of the rupture relative to the along the strike and down deep. And so the area here will give you all the admissible positions that you can have for the rupture, but in terms of the likelihood of which one of them, you need to define a distribution. So I think we already saw that, for example, for the down dip, you can assume that there is like either a uniform distribution or some type of like triangular distribution where it's more likely to have like the rupture concentrated at depth. Same thing along the strike of the fault. So you can assume that it's uniform, or if you know that there is some higher some location where it's more likely for the rupture to be located. And if you have, so these parameters are parameters that you need to define both if you are dealing with like well-specified faults that you know the geometry, or if you have like background zones where, like if you remember from the example that we saw, we define a zone like a polygon, and we say an earthquake can be located anywhere there. So in that, if that's your polygon, let's say, and your site is located somewhere here, you can assume every point in this polygon has an equal likelihood of accommodating an earthquake, and so you define the distribution by assuming its location in the polygon is equal, or you can have some distribution that says, okay, we don't know where exactly the faults are, but most likely they will be located in this corner of the polygon versus some other. And all of this is information that typically you get from a geologist that typically is involved in these types of projects and helps you to do the seismic source characterization. And then the final the information that you need is to define the geometry. So the coordinates for the top of the fault, its deep angle, its maximum width, and how deep the fault is. Like some faults can reach the surface, and so in that case, the depth to the top of the fault will be 0, but some faults are buried. So in that case, you will say that maybe like the fault starts like 3 kilometers below the Earth's surface, and this information will be used to calculate the distances. So this is the general information. So now let's see how all of this information will go into the input file. So this is like a screenshot of how like the input file should look like. So the first line is you need to specify what coordinates you will be using. So whether you will use X and Y coordinates or whether you will define everything in longitude and latitude, because depending on how you define it, like you need different formulas to calculate the distance. And then you need to define how many faults and background zones here that you will have. So you may say that, so one of the, like this program works in the command line, so there's no user interface. You need to write like a text file, a simple plain text file with the information, then it will be inserted. So in this case, let's say that we want to evaluate 2 faults. So then after that, we will go through the information that needs to be defined for each of the faults. The first line for each fault is the name of the fault that you have and the probability of activity. So this is a probability that is applied to the activity rate. That's because you can have you may have a fault, but you may have different alternative definitions of the fault that you like. You can have the Hayward fault, but not really know its full geometry. So you can assign like a probability of 0.5 for one realization of the Hayward fault and define its geometry, and also assign the probability of 0.5 for the second definition of its geometry. So this is to allow you to essentially account for the same fault, to define the same fault more than once, to account for any epistemic uncertainty that may be coming from that. Then you will define how many segments that this geometry has. So this is essentially how many parts of the fault could rupture and in what style. So you need to define how many segments and then how many source realizations you have. So the segments is all the different parts of the model that the fault that you have, and the number of sources is all the different ways that these segments could rupture together or alone. So for example, you can have, like if you were to say that you have 3 segments, like this is segment 1, segment 2, and segment 3, you can say that there may be, so in this case, n seg will be 3. But the number of the total sources, for example, could be 5, because you can have segment 1 rupturing on its own, segment 2 rupturing on its own, segment 3 rupturing on its own, but maybe also 1 and 2 rupturing together, and 1, 2, and 3 rupturing together. That will be like 4, 5 sources. So you can have 6 sources where you also have the case and 2 and 3 are rupturing together. And this is again information that you typically get. So you can have 1, segment 2, segment 2, 3, 1 plus 2, and 1 plus 2 plus 3. And with and with this, and in this line, you will essentially define the different segmentations that you have. So the way that you will codify this is that you will have, like, you will say the total number of sources is 5, and then you will say the first source is 1, 0, 0, the second is 0, 1, 0, then you have 0, 0, 1, and then you have 1, 1, 0, and 1, 1, 1. So these are like the segments that are activated in each source that you want to evaluate. And then you will go and define each of these segments. So you have so I'm going through the manual so that you're familiar, but I also have its manual on UBLearn. So here I created this folder, and you have the manual for how to construct this input file, and I will also give you an example. And then I compiled it for Windows, Mac OS, and Linux. So it should work, but and I also have the source code, so you can also compile it yourself if you are interested in. But you should have like the executable files to run this. So then the next thing that you need to do is define the information about each segment. So here we have one segment, so we only need to repeat this thing once. For each segment, we specify its source type. So this is one if it's like a linear fault, like a well-defined fault, and it will be two if it's a background zone where we define the polygon. Then we can have the attenuation type. And this is to differentiate between sources that are of like that go with different ground motion models. So you may want to group all like shallow crustal sources as attenuation type 1 and all subduction zones as attenuation type 2 if you are in an area that you have both sources contributing to your hazard, because you don't want to use a ground motion model for shallow crustal events on a subduction zone and the opposite. And then you define the step size. So how finely you want to sample that faulting space. So here is every 100 meters. And then we have the segmentation. So you will also define the weight. So how likely this segmentation is relative to the errors. Then, as we said, we define the deep angle for that fault and the depth to the top of rupture. So in this case, this is a vertical fault, and the top of the rupture reaches the surface. After that, you define how many points you will use to define its geometry. So it's a long strike geometry, and these are the latitude longitude pairs that you use to define sort of points that, if they are connected, define the surface projection of the fault. And then you can start having alternative realizations for how you define the geometry. So you define that the sort of deep angle the reference deep angle that you will use is 90 degrees, and then you can define variations around that. So you say that like sort of part of your epistemic uncertainty. So part of the uncertainty that you have in how well you have characterized this world is that this may be 80 degrees dipping to the west, or zero, so vertical, so like 90 minus 10, like 80 degrees dipping to the west, or vertical, or 80 degrees dipping to the east, with weights 0.2, 0.6, and 0.2 to give like some uncertainty on how its geometry is defined. And same thing for the b value that is used in the recurrence model. So again, you can say I don't really know what is the slope of the magnitude recurrence relationship, so I'm going to use 3 being 0.8, 0.9, and 1, and assign weights of 0.2, 0.6, and 0.2 again. Then you can define so how many activity here in this case the magnitude. So in this case you will say that I will define you can we saw that you can define the activity rate either in terms of its slip rate or in terms of like the activity rate that comes from historical seismicity or by paleoseismic through a paleoseismic study. And this is how you assign the weights for each way you are going to define the activity rate. So you say I assign in this case 80% to defining the activity rate through a slip rate, and 20% defining the activity rate by directly knowing the recurrence interval through a paleoseismic study. And then you define how many possible values of slip rate you have. So it can be 7, 9, and 11 millimeters per year, and the weight associated with each of these values, or the recurrence interval that you have. So this will be 100, 120, or 150 years, and the weight that goes with each of these numbers. So this will be if you have done some trenching and you found like you were able to go through essentially, I don't know, 300 years of ruptures, but you are not really sure if like it's 300 years, so like, and you have the event, so you have a mean recurrence interval of 100 years, or only two of the scarps that you see are actually associated with tectonic faults, and that there is something else, or some alternative interpretation of the data that you have.
Activity rate, isn't it for a particular magnitude and distance there? For a fault?
It's for the fault itself. The distance it depends both on the site and the fault, right? Or what do you mean?
So like in the assignment problem, we were given m comma r, and we were given a particular activity rate for that m comma.
Yes. Do I have the minimum magnitude here? Let's see. Yes. So wait, I confused. We were here. So the activity rate that you define, if you remember with what you did, that goes with the minimum magnitude, right? So here you will not assume a single magnitude, but a full distribution. So the activity rate will be with the minimum. The distance is not associated with a fault because the distance is the distance between the site and the fault itself. And again, instead of assuming that we have fully defined the rupture, so it's not allowed to move, we assigned. Have we done? No. We will see. We will define the distribution for where the rupture is located, and so the distance will be calculated internally to evaluate the ground motion model.
Activity rate here is the mean annual number of earthquakes of magnitude greater than equal to 0.
Okay, so here you define what the minimum magnitude is. So since we defined here that the minimum magnitude was 5, the activity rates that we defined were for 5. But if you set this to 0, then you would need to change the activity rates respectively. Any other questions? At least, do you see the connection between what we have been covering and how you will sort of use all of this information to do this analysis? So, and you will continue with quantifying all of the uncertainties. So, again, the number of logic tree branches that you will have for the width, what are the values of the width, and what is the weight associated with each one. Same thing for your characteristic magnitude number, for how many characteristic magnitudes you will use, what's the weight, and what is the maximum magnitude. And typically, if you remember, we saw that like the characteristic and the characteristic is typically like 0.2 or times what the maximum magnitude is 0.2 or 0.1 magnitude units larger than the characteristic. So in this case, and you will do this for which width that you define. And why is that? So we said, if you remember that we said that the maximum magnitude that we can have, or the characteristic magnitude that we can have is m is log of a minus 4, right? So, and a is, so from here, we already defined the length of the fault. This is if you follow, like, this will define some type of a fault trace that may go something like this. So each point defines like the vertex for this polyline. So you can measure the length of your fault trace. But then you have different different realizations for your fault width. So if you multiply the single value for the length, which is possible number, you can have different maximum magnitudes that will go with each one of them. And that's why you are allowed to enter a maximum magnitude that will go for each value of width that you will insert. And so as so as the width of the fault is increasing, you are allowing for large possible magnitudes to occur. And then last, you will define sort of the mean magnitude from which you will do the integration for all the possible magnitudes, how finally you will discretize the magnitude, the stepping size in along stride and along the vertical direction, and then how many realizations, how many samples you will create to generate the rupture, the area of the rupture associated with its magnitude, and the width associated with its magnitude. So here you will say that this is to define a relationship that is where you have log of A is some value C1 plus C2 times m. So this value specifies the value for the constant, and this value specifies the value for the slope. So we said like before we were using that log A is n minus 4, like this is sort of this comes from a model that like actually tried to fit some data, and you see it's close to the theoretical one, but there is some deviation. So you have the flexibility to choose your actual relationship. And same thing for the width. So you can again define some relationship that will be log of W is C1 plus times M, and these are the values that we go for the constant and the slope. And then here, since you only specified that you will sample these relationships one time, it's not going to use the standard deviation of the model. But if you were to define it, like you say, like sample each area and its width, like, I don't know, 3 times, then it will go and it will be the mean value and then plus minus sigma, and then assign a weight, like the weights in order to approximate a normal distribution. So this is if you want to also account for the variability in the area of the rupture and the width of the rupture. Maybe one more slide and then we can stop. So this will be your source file that you will do to define each source, and I think I will give you most sources defined, and then I will ask you to just modify one of them. So that was one of the file. And then you also have to, no, this is not the full file, this is the ground motion file. So in the ground motion file, you will specify the name of the source file that you want to read, the version of hash you will be using, the maximum distance, like because you can have a huge file that includes, I don't know, faults that go from Los Angeles or from San Diego to Oregon, but you only want to include the faults that are, let's say, within 1,000 kilometers around your site, because those are the ones that contribute. And then how many periods you want to evaluate, or yeah, maybe we are on time, so I think it won't be rushed if maybe on Monday we go through that, and then we can go through actually running the hazard code. But the goal is sort of like all of the material that we are going is sort of to have an understanding, like how do you set up a problem like this, and what is the information that you need to have to essentially run a seismic hazard calculation. Any like last minute questions that anyone may have? Okay, then I will see you on Monday.